Okay, so let's talk about problems with measurements. So let me start this slideshow. Okay. And the first most obvious question is probably why are there problems with measurements, right? So a couple things that can be an issue. Number one, the person making the measurement could not be good at their job, right? Or the measurement that they are making could be dependent on a lot of outside factors, okay, that are not, within their control. So if we look at this fourth picture right here, this is an electron microscope, and it is very sensitive to vibrations, right? Because the things that you're looking at are really small. So if someone in the building slams a door, and the electron microscope is not properly insulated, that could actually be enough to mess up a measurement that's going on in there. Another one is the conditions of the measurement, right? So things like humidity. This is a ground-based telescope, okay? And when you think about it, right, there's a little tripod and the telescope, okay? And it's, looking at where it thinks the star is up here. And the problem with ground-based telescope is our atmosphere is in the way, okay? So, whoa, what happened? There we go. Our atmosphere is in the way. Apparently this writing pad, not a big fan of dots, all right? So the atmosphere is full of gas. Now, light from my star is moving right through space. And when it hits that gas in the atmosphere, it bends. Okay, so the person who's making the measurement says, oh, well, the star is actually up here, right? It's following this line of sight, but that's not really where the star is. Now, it's normally not this quite drastic, okay, but because of the words, I had to get out of the way. So the conditions of your measurement can mess with the measurement. If you look at the Hubble Space Telescope, which is over here, the Hubble Space Telescope, it's out here in space, and it's huge. It's got these big solar panels like that, and it can look right at the star. So it says, hey, star's right here. You're on the ground. You're like, hey, star's right there. Well, this big distance in the middle, that's your error, okay? So there can be lots of reasons for error. The other thing that can be, an issue is the actual measurement itself, the instrument that's making the measurement. So you look, if you zoom in at this ruler, what if something falls directly on the black tick mark? So is an eighth of an inch up to the black tick mark? Is it up to and including the black tick mark? Is it up to but not quite touching the black tick mark, right? So all of those things, although they're really small, could be issues with a measurement, all right? So some of the ways we classify those things, we use two words. We use accuracy and we use precision. Accuracy is probably the one that we're most familiar with, because if you get an accurate number, then you know the number is correct. It is close to the true value or the accepted value of a measurement. A precise measurement does not have to be accurate, and we can see that right here. So this is a precise measurement that's not accurate. It's very far from the true value, right, the bullseye, okay, but it's precise because all four of the measurements are close together. Now, if you're not accurate or precise, you end up with something like this, right, where we have four measurements and they're all over the place. And this really shows us the reason why we use averages. So if you were to average these measurements, you would probably get something right around here, which is way better than any of the individual measurements, right? But in all, because they're so far apart, we know that they're not good measurements. We need to reassess our measuring tool or our measuring method. Now, in order to talk about error, we use percent error, okay? And percent error tells you how far away from the actual value you are. So it's like, how wrong are you? And there's a lot of different ways you'll see it written. I think it's written in this yellow in the textbook. But basically, it's E minus A over A times 100. So E is the experimental value. All right, so that right there, this number comes from an experiment. Number from an experiment, which implies, all right, It is a measurement. Okay. That's what it is. A, okay, is our accepted value. So, whoa, what is going on there? I don't know why it keeps doing that. A is our accepted value. Okay, so this is the true value. Okay, sometimes we say the true value, and it usually comes from the problem. Now you can calculate the accepted value if you know your percent error. That would be really uncommon. Okay, and notice that you use it twice. This is the same number. All right. Why might you want percent error? Okay, there's a lot of reasons you might want some percent error. Number one, if I have you doing a lab and I say, okay, you should get 2 grams of product. You make 9 grams of product. That doesn't mean you did a really good job. In fact, that means you really did a bad job. So if in your experiment you made 9 grams and I said you should have made 2 grams, well, we do our little math problem here. We get 7 over 2 times 100. All right. So 7 halves, that's 3.5. You have a 350% error. So that's really, 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 really bad. And it's positive, like you're over 350% what you should be. So it gives you an idea when you're doing a lab prep if you're close to what you should be doing. On the other hand, right, if you make 1.97 grams, you're going to have a really low percent error, which probably means you did a good job. So you can use percent error to intuit the outcome of your experiment. If you mixed, 2 grams of X and 2 grams of Y, and you end up with 9 grams of Z, and the lab prep says you should have 2, you know something's wrong, right? So we want to have a way to categorize and even quantify our laboratory outcomes. So that's what we use percent error for. And we'll see it some more in the springtime when we get to stoichiometry. But for now, we just want to know this equation. Now, something else with measurements, and this is the big thing we're going to talk about with measurements, is our Sig Figs, okay? And significant figures, or Sig Figs, is a system that lets us look at a number from a measurement and tell how accurate it is. So first, let's identify the fact that there are 2 kinds of numbers. You have exact numbers and you have measured numbers. Exact numbers are exact, okay? They are specific to a certain number of digits or a certain number of decimals because they are defined numbers. One way you could look at that is like a defined 1 grams in a kilogram, or there are 12 inches in a foot. It's exactly 12 inches. It's not 12.00001, all right, inches in a foot. It's exactly 12. Anything else, okay, would be a measured number, all right? And measured numbers always have some error. It depends on what your tool is that you're using. So let's just kind of look at a couple of these first. And let's tell the difference between exact numbers when, you just report the number as it is compared to a number where we have to take Sig Figs into account. So counting numbers, always exact. If I look over and I see 2 soccer balls, there's exactly 2. I can't have part of a soccer ball laying there. If I have 4 pizzas, I either have 4 pizzas or I don't. Like we said a second ago, if we have relationships, they're predefined. You don't measure them. They're just true statements. Like a foot is 12 inches or a meter is 100 centimeters. Those things are exact numbers. You don't have to worry about there being a bunch of decimals and then a 1. We know it's exactly 12 inches, okay? Now, something I like to kind of run through your head, a different way to think about this. If I asked you how to get an exact number, what would you say? Would you use a measuring tool? Would you count? Or would you use a definition? Well, if I'm measuring, I know that the tool, just because it's man-made, is not infinitely accurate. So if it's not infinitely accurate, it can't be exact. So it can't be number 1. If I count, I can get exactly 2. So that can work. All right. And if I know a definition that says this is equal to that, that can also work. So it would be these 2. Obviously, if you flip that question around and you say, how do you obtain a measured number? Well, counting is exact. So it's not measuring, and a definition is exact. So it can't be. But a measuring tool definitely gives you a measurement. All right. So that would be something, a different way to kind of think about it. Now, if I give you some examples of relationships between numbers and said, hey, tell me if this is exact or tell me if it's measured, you should be able to do that too. So, for example, is a yard 3 feet? Well, yeah, it is. So how do we know that? It's defined. So if 1 yard equals 3 feet, and we know that this is the definition of a yard, then we would say that this is an exact relationship. It's an infinitely significant number, okay? What if we said the diameter of a red blood cell is 6 times 10 to the negative fourth centimeters? All right, well, how do you find diameter? Well, if I want to find diameter, I have to measure, okay? And so this would be a measurement. If I'm using a measuring tool, then it's not exact. So this is a measurement. So it's not infinitely accurate. What if we say there are 6 hats on the shelf? Well, there's no tool that, measures hats on a shelf. This would be counting. So in counting, all right, I'm going to get an exact number. Gold melts at 1,064 degrees Celsius. Well, this is actually a measurement. And I know that it's a measurement because I have degrees Celsius, which tells me I was using a thermometer. And if I'm using a thermometer, then I must be taking a measurement. Now, this one is interesting because this is a definition. That is the melting point of gold. However, it's not the defined relationship between two numbers, so we don't consider it to be an exact number. All right. So we have two exact numbers there, 1 and 3, 2 counted numbers. So let's look at the measuring numbers because exact numbers are easy. You just report them as they are. 2 hats, 6 balls, 75 pizzas, whatever it is. So here's an example where I have to make Sig Figs come into play, and you'll actually see what they do in practice. So I have a graduated cylinder here, and it's zoomed in. And when we read a graduated cylinder, we always read the meniscus, which is, right there in the middle. And we can see that it's between these 2 tick marks, all right? It's definitely, between 15 and 20. So we have 16 here, we have 17 here, we have 18, and then we have 19. So if I want to report what this number is, then I look at the meniscus. I know it's at least 17, so we've started it here. And the question is, what do I put in this blank? And this is where Sig Figs become actually really important to science. I have to guess, all right? So I need to guess as best as I can what digit I would get. So I could have 17.1, 17.2, 3, 4, 5, 6, 7, 8, 9, 10, whatever it is. I need to guess. It looks about halfway to me. So I'm going to say, all right, in this question mark, I'm going to say 17.5 milliliters. Now, here's why Sig Figs are important. And this is the thing you need to understand. Anytime you look at a measured number, the last digit is always a guess. And the more digits that you have, the more accurate, all right, and for the more expensive, the measuring tool is. So when you're in math class and the teacher says, hey, look, don't give me, calculator overflow. I don't want to see 17.59736, yada, yada, yada. The reason for that is we don't really have a lot of measuring tools that can go to that many decimals. This is, I wouldn't say an expensive graduated cylinder, but when you start adding decimals of accuracy, you start to get very expensive very quick, okay? So when you look at a measurement, know that the last digit is always a guess, and that tells you how accurate your measurements are. If, you're reading a scientific paper and the most accurate number they have is like 17 milliliters, well, that tells you that their graduated cylinder went from 10 to 20. Because this digit, the 1, is certain, but the last digit is a guess. And if the best graduated cylinder that you can buy only has the tens place marked, you're not doing a very scientific investigation. All right, so this would be bad. This would be not very accurate. But on the other hand, if you're reading something that's like, we had 17.673 milliliters, all right, well, now you've got your tens places marked, right? So this is marked, your ones are marked, your tenths and your 100ths are marked. So that means this graduated cylinder is accurate to 1/100th of a milliliter. A milliliter is like a teardrop. So imagine cutting a teardrop into 100 pieces. You have a graduated cylinder with lines far enough apart, or I guess close enough together, to measure 1/100th of a teardrop. Yeah, that's pretty accurate, all right? But again, even looking at this number, I know that that last digit is a guess. It has to be a guess. It's always a guess. So we can try some of those, right? We look at this. We know that the marking is between 1.6 and 1.7 centimeters, right? So I can count those off. 2, 3, 4, 5, 6, 7, 8, 9. What in the world? Oh, sorry. 1.1, 2, 3. There we go. 4. Come on, pen, catch up. 5, 6. There we go. 7, 8, 9, and 10 millimeters would make the second centimeter. There we go. I was like, what in the world is going on? All right. We know we can't see anything between this 0.6 and 0.7. So there's nothing here. We have no tick marks. So that's where our guess has to go. So we know we can say we got the 1. We know it's definitely past 1 centimeter. We're good there. We know it's not all the way to 2, so we can't go 2. All right. So we say 1 point. We can see the 6. So we're definitely past the 6. 6. And so this last digit will need to be our guess. And here's the cool thing. I'm going to say it's 1.67. You could say 1.65. You could say 1.61. Whatever you think it is, the last digit is known to be a guess. And so it's up to the researcher. All right. It's up to the scientist. Okay. So that's what we would get. All right. You never go past the guess, right? So keep that in mind. The last digit's the guess, not the last two. So here's another one, all right? Would it be 4.5, 4.54, or 4.547? Now, this is a multiple choice, test question. Easy way to do this, all right? Look at it in terms of how many digits we've got, and then compare it to how many digits are shown on your ruler. So do I have a ones place? Well, yeah, absolutely. 1, 2, 3, 4. Got the ones place. We know we're through to 4, so this one's good. But if this second, digit, our last digit, number 1, is a guess, there couldn't be anything in between them. So it can't be number 1. I look at 2, 4.54. Well, do I have the 4? Yeah, I got the ones place. Yep, we're good. Do I have the tenths place? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, got the tenths place, so my millimeters are there. So I'm good with that one. So is the 4 a guess? Well, yeah, I don't have anything between there, so the 4 must be a guess. Well, that already tells me it can't be this one, because I would have to have the tenths, or the ones place, the tenths place, the hundredths place, sorry, and we'd be guessing on the thousands. So we have to rule that one out. So we would say it is number 2. Okay. What would this one be? All right, now remember, we're in science class. So we don't care about inches. We're looking at centimeters. All right, we use the metric system. So we definitely want to be there. So we're looking at the end of the pencil. We're right at 8. So do we say 8, 8.0, 8.00? All right, what do we do? Well, we have the ones place, so we definitely are going to write the ones place. We have a tenths place, so we have to write the tenths place. We don't have a hundredths, so our last digit is a guess, and I always have to have a unit. So 8 centimeters it is. All right, so that's how you make a measurement. Okay, that's how we know how many digits to go to. Whenever we look at those digits, all right, and this just kind of sums those things up, just make sure all of the digits are all of the digits but the last one are certain. Okay, you can point to something on the measuring tool and say, yes, here's the mark for that unit. Remember that the last digit is uncertain, and so the more digits you have, the more accurate your tool must be. Keep in mind, all right, it's a pretty good measurement. That's pretty cheap, though, as far as the scale. We have these in the lab. This is a super accurate measurement, all right? we've got tenths, hundred thousandths, 10,000ths, 100,000ths place, all right? So we are, plus or minus 100,000th of a gram. We're up here, we're plus or minus a centigram, right? 100th of a gram. So big difference, okay? Now, when you're examining numbers, not every digit in a number is significant, okay? All of the digits 1 through 9 are always significant. All right, always significant. All right, now take a little brain break here. We're kind of switching gears. So we talked about measurement. Now we're going to talk about actually analyzing these numbers. So if you need a minute, pause the video, walk away, come back. All right, we want to examine the number itself. Okay, so picking up where we were. When you're looking at a measured number, all of the non-zero digits, so the digits 1 through 9, they're always significant. However, 0 doesn't necessarily have to be significant. Sometimes it's a placeholder. So there are 4 rules that tell us if a 0, is significant. So the first rule, all right, we'd like to call this the sandwich rule. All right, sandwich rule. If you have zeros in the middle of a number, then they are significant. So if I say, how many significant digits are in the number 101, we would say 3. I know that because 1 is always significant because it's a number 1 through 9. And this 0, all right, is sandwiched in the middle of them. So I know it counts. So it's happy, it counts. We have 3, and we would say Sig Figs. 3 Sig Figs. Okay, if you have a number like 1,001, well, that one's significant, that one's significant. So both of these guys are sandwiched in the middle. So that has 4 Sig Figs. Okay, and so on and so forth. It doesn't matter how many digits there are. If they're sandwiched in the middle, then they count. They're significant. Rule 2, it talks about the zeros at the beginning of a number. All right, so this is called a leading 0. Leading 0 rule. All right, and it says if you have numbers at the front of a number, they don't count, so they're not significant. And the reason for that is there's no measuring tool that's going to tell you something is 0.00001 centimeters. The zeros out front, they're irrelevant. You can leave them off. Okay, so if I look at a number like this, 0.029, right? It's the one that we have up here, 07. Well, this zero are leading zeros. There's nothing significant out front. And so they don't count. They're just acting as placeholders. Non-zero numbers are always significant. And we have 1 0 that's sandwiched. All the rules work all the time. So since this 0 is sandwiched, it counts. So this would have 4 Sig Figs. All right, so those are the first 2 rules. We have the sandwich rule, we have the leading 0 rule. Rule 3 talks about trailing zeros, okay? So rule 3 is our trailing 0. Oof, it's a rough Z. Trailing 0 rule, okay? And it says that if you have zeros at the end of a number and the big key here is and, after the decimal, then they are significant. And the reason that they have to be after the decimal is because we just talked about making measurements, and we know that if there are a bunch of digits after the decimal, then they're there for a reason. So if we look at this number here, we have 138.200, and I'm going to change it from meters to milliliters just to make it, more like the conversation we just had. So here's my graduated cylinder. I'm telling you that the 1, the 3, the 8, the 2, they're all significant because they're non-zero. But this number, it's after a decimal and after a number. So it's a trailing 0. Well, I'm telling you, hey, we've got the tick mark for this one too, and it's a 0, so it counts. So this one must be my guess, and it's at the end. It's a trailing 0. It's after a number and it's after a decimal. And when we say at the end of a number, this is a 1 through 9 number, like after a significant digit. It could be, 1,001.000. It could be 999,000, right? 0.000. The zeros are still after a number and after a decimal, so they count. All right, so this would have all 6 of these would count, as it says right there. All right. The last rule is the zeros at the end of a number and before an implied decimal point may or may not be significant. So this is kind of our iffy rule. All right. It doesn't have a catchy name like this. It's just the 4th rule. All right. You don't really see this very often. Okay. At least you won't see it in my class, where you get zeros at the end of a number before an implied decimal, and I go, hey, what's significant? So what would that look like? Well, let's say I said 101, and then we added a 0 on there, so we're going to say 1,010. So we know the ones are significant. We know this 0 is good because it's sandwiched, so we know we have at least 3. But the question is that 0 right there a placeholder? Or is that 0 right there significant? Well, we don't actually know, right? It could be to define where an unwritten decimal is, right? Because there is a decimal point right there in theory. But without that decimal there, that unwritten decimal point, we don't know. So we would just say, more than likely, this just has 3 sig figs. I'm not going to give you any problems like that because it is a rule that depends on the science that you're doing and the math that you're doing. So we might see this one, and if we do, we'll talk about it, but not one I'm going to give you on a test. However, it does bring up something that I don't actually have in the PowerPoint I'd just like to talk about. It's the bookend rule, okay? So the bookend rule actually is the other part of this, and I feel like it makes it a little easier to understand. So if we look at these 2 numbers, notice that one of them, we'll say number A, like the first one here, does not have a decimal point, and B has a decimal point. And whenever you see a number followed by a decimal point, you read that decimal point as the word exact or exactly. So this number is 1,010 exact. This number is 1,010. So here, we still have 3 sig figs. In this case, this decimal acts as a bookend. And so the bookend rule works with the sandwich rule. I've got a 1 out front, got a 1 right there, so we know the sandwich rule is alive and well there. But now we're going to say this decimal is a bookend. So any 0 sandwiched between the bookend and a non-zero number is also going to count. And so this one would have 4 sig figs. Okay. So those are the rules. You have 4 rules and then kind of a half rule, right? The bookend rule. Okay. And that kind of helps us tell the difference between the may or may not. If the decimal is written, it counts. If the decimal is not written, then that 0 does not count. Okay. And that's the difference in the 2. So let's look at some of these. In the first one, you don't have any zeros. So that means every digit must count. There are 6 sig figs. Okay. In the second one, all right, I'll give you a second. See what rule you think applies. It would be the leading 0 rule. We know leading zeros don't count, so the zeros out front are not significant. There are 3. All right. In the third one, we have 2 rules that we need. First is the leading zeros, and the leading zeros, again, tell us those don't matter, but this is my trailing 0. It's after a number, and it's after a decimal, so they must be worthwhile. So we have 5 sig figs. All right, 48,000 exactly. All right, that should be the big key there. It's the bookend rule. So all 5 of them count. And the next one we have 48,000. Well, all right, our trailing zeros that come before a decimal, all right, they don't count. So we only have 2, the 4 and the 8. Now the next one's scientific notation. We haven't really talked about that. All right, so think about it for a minute. Do you think the scientific notation matters, or do you think it doesn't? Well, in fact, it does not. So we say that the digits of the number are the things that come before the times 10 to the whatever. So this part of scientific notation, it doesn't count. We never, ever, ever look at it. All right, it doesn't give us digits. These are the digits in the number, and so we've reported it to 4 sig figs, and that's what you have. And the last one, all right, we have 2 rules again. All right, I'll give you a second, see if you can figure them out. I'll start drawing. So this rule would be the sandwich rule. And this 0 also counts because it's a trailing 0, which is both after number and after decimal, so all of them count. Okay, why do we need these? What's the point of having a sig fig rule? Well, we use them in calculations because here's the deal. In your experiments, the best number you have is irrelevant, okay? Your experiment is only as good as your worst measurement. So our sig figs tell us which measurement is the least accurate. And whenever we put measurements together, they can't end up with an answer, with a number, like with a product or a quotient or a sum or a difference that is more accurate than one of the parent numbers. So the more sig figs there are, the more accurate your number is, but the less sig figs there are, the worse off your experiment outcome is going to be. So if I want to divide or I want to multiply, it's the same rule, okay? Then I have to look at the total number of sig figs in the least accurate number. So on top, I've got 3 sig figs. I got 3 non-zero numbers. So here we have 3 sig figs. On the bottom, I have 4 sig figs. Well, my answer cannot have more sig figs than either of the original numbers. In other words, you have to have the fewest number of sig figs in the answers that were in the problem. Here's 3, here's 4, I gotta go with 3, so I have to round it. All right, now let me pull out a calculator really quick. If I actually do this problem, okay, in my calculator, then if I can get my calculator to work, 278 divided by 11.7, 278 divided by 11.70, this is the number that I actually get, 23.7606838. Now, this is your calculator overflow, your calculator diarrhea. This is what we don't want. So I go, okay, here's 3. So I go 1, 2, 3. So that's where I have to stop. So this is where we round. So I look at the digit where I have to stop. It's a 6. Anything bigger than 5 or bigger rounds up. So this 7 becomes an 8. So I round it. And I know to round it at 3 sig figs. So we're going to say round at 3 sig figs. All right, and that gives me the answer that I actually report. And it takes in the measure miles was not very accurate. This is a terrible measurement for miles. It means it's only good to the ones place. So, you know, it could have been 278.4 miles, or it could have been 277.5 miles. There's like plus or minus basically a half mile in here. That's not a very good accurate. I mean, a half mile is a long way. So I have to take that into account when I report, in this case, how many miles per gallon I get. So that's multiplying and dividing. I look at the whole number. If I'm doing addition and subtraction, I look only at the number of digits after the decimal point. So in these two numbers, I'm adding 3.18 to 0.01315. I count digits. Well, here I've got 2 digits after the decimal place. Here I've got 5. So my answer can only have 2 digits after the decimal place because, again, I'm going with the fewest number, okay? And so I round and I move on. All right, the 3 that comes down, right, because these are question marks here, these would all be treated as a 0. So I would have 5, 1, and 3. Well, I have to stop at 2. The 3 does not round me up, so I say at 3.19. Now, let's say it did round me up. Would I report 3.2? Well, no, I still need to have 2 decimals, so I would say 3.20, right? That way I still have my 2 digits after the decimal point. So if it did round you up, don't forget to include your 0. And of course, you have to have a unit. Here are some practice ones for you guys to try. All right, so I'm giving you the answers. We need to figure out where to round. So I have multiplication. So I'm looking at the whole number, 4 non-zero digits. So that has 4. Here's 3. So I want to go with 3 because that's the lowest number. So I count from the left, 1, 2, 3. Does that round me up? Right. So I'm looking at the 9 and I say, do I round up? The answer is, of course, yes. So I would get 49.7. Right. Next one, I have 3 here. This is a leading 0, doesn't count. So I have 1, 2, 3, 4. So my least number is 3. 1, 2, 3. Does the 3 round me up? All right, I just look at the next digit. 3 does not round you up, right? Only 5 or better. So I stop at 46.4. Okay. You guys get the idea, right? Look down here at this last one real quick. Okay, I'll let you can work these out on your own. Make sure you get the same answers I get. Here we have exponential notation, right? Scientific notation. Remember, these don't come into account. So I have 1, 2, 3, 4. Remember, this 0 counts because of the sandwich rule. 1, 2, 3, 4. All right. Well, if I have 4 in both, well, then the fewest number of sig figs is 4. So when I multiply these things, I get 1.0000. Well, my leading 0, or sorry, my trailing 0 says after a whole number or after a non-zero number and after a decimal, all those zeros count. So I have 4 right there. All right, I'll let you do the same thing with addition and subtraction. Remember, it's digits after the decimal. So you can draw a line, you can picture it, whatever you need to do. Okay, top number only has 1, bottom number has 3. So I do my whole math problem and then I round. I'm going to round after 1 decimal place. It definitely rounds up. There we are. All right, you can work these. Just make sure you get the same answers. All right. More stuff right here. Okay, more practice for you. I'll let you look at those. If you have a mixed order of operations, follow the order of operations, all right? And don't round until you get to the very end. So I do my first step. I'm going to do my multiplication. So these two things, all right? I get to the end of my multiplication. I need to round. This has 4 sig figs in it. This has 5. So this answer should have 4. Now I'm adding 1 digit after the decimal, 2 digits after the decimal, 3 digits. So I got to go with 1 digit after the decimal, all right? And that's where I round it. So here's my 1 digit. I look at the next one. I say, hey, does that round me up? No, it doesn't. So I stay at 0.6. All right, same thing down here. I'm doing order of operations, parentheses first. So I'm adding. So 2 decimal points. This has 4. Got to go with 2. All right, so the answer to this should have 2 decimals. This has 2. This has 1. The answer to that should have 1 decimal. Sure enough. This has 2 decimals. 1, 2. Now I've got 4 total sig figs. This has 4 total sig figs. So I need 1, 2, 3, 4 in my answer. Does that round me up? Absolutely. So there we go. All right. When you look at scientific notation, all right, take some time to read through this. I think you guys have done scientific notation before. If you need some review of this, I'll be talking about it later in the week. All right, but read through these notes on scientific notation. I trust that you've done that before. All right, so I'm going to kind of skip through that for now. Same thing with rounding. I think you guys know that 5 and up rounds a number up. 4 and below keeps the number the same. Remember, you never round down. You're not going to change your number to a smaller number. All right, so I'll let you guys read those and, walk through the practice if you need it, okay? So there's a bunch of those in there that are extra, all right? Let me stop presenting here. Maybe. There we go. If you have questions, ask them in the office hours, shoot me an email, whatever. I'll see if I can help you out. But again, as you watch these videos, I know that they're long. We're covering a tremendous amount of material. You have all week to get through some of these, so you do not have to watch them all at once. Okay, break them up into, manageable chunks. Stay on top of your problem set. Stay on top of the review that's at the end of the week. Remember, the goal is to not have any work to do on the weekend. So stick to the schedule and let me know if you have questions. All right. I'll see you guys in the next one.